So in this video we are going to talk about behavior of viscous fluid while it is flowing between two parallel plates. While studying this scenario, of viscous fluid flow, we need to look at the various parameters of flow. So in this case, we are going to see the first one is the velocity distribution, the second is the ratio of maximum velocity to average velocity, third is drop of pressure rate between two sections of the parallel plates, and the fourth one is shear stress distribution. So these are the 4 points what we are going to study in this section. So while studying this scenario, we need to make some assumptions. So let's consider the plate 1 and the plate 2. The both plates are the parallel and they are kept a distance t away from each other. And the viscous fluid is flowing from left to right, as you can see in this animation. In order to study the behavior of viscous fluid while flowing between two parallel plates, we need to assume one fluid element between two parallel plates which are the t distance away from each other. So we'll take this fluid element of a rectangle shape, call it as a ABCD. So on these fluid elements, which is having the dimension of delta x in the x direction, thickness delta y in the y direction, and this fluid element will be at a distance y from this lower plate. Here you can see. So let us assume that on the face AB of this fluid element, the pressure intensity P is acting. Similarly, the pressure intensity of P plus delta P by delta X into delta X is acting on the face DC. This is face DC and this pressure is acting on this face. And on the face BC, the shear trace is acting in the direction opposite to that of flow, and similarly on the face AD, the shear trace is acting in the direction of flow. That too is acting on the face AD, as you can see in the figure. If we consider this whole figure in the Cartesian coordinate system, and this will be the y-axis and this is a x-axis, and the width of this fluid element will consider the unit in the direction of plane perpendicular to the plane of paper. So when we are considering the one fluid elements, there are the number of forces acting on the fluid elements simultaneously. So in this, if you assume that the pressure P is acting on this face AB, then the entire pressure force acting on the face will be pressure into the area of AB. So here you can see the pressure into the area of face is delta y into 1, and this pressure force acting on the face AB. Similarly, the pressure force acting on the face DC is P into plus delta P by delta X into delta X into area. This one is the area. This entire pressure force is acting on this face DC. So this variation in this pressure is because of this length of fluid element, or you can see because of the cross section of fluid elements. So this pressure from one end to another end will get vary by this amount. So these are the equation we can derive from the Taylor equations. So similarly, on the face BC, the shear force because of the shear trace tau is acting, and it will be equal to shear trace into the delta x into 1. Delta x into 1 is nothing but the area of BC. So here you can see this shear force is acting on this face BC. Similarly, on the face AD, the shear force, another shear force is acting, that is tau plus delta tau by delta y into delta y, and the whole bracket is multiplied by this area. Area is nothing but delta x into 1. So as we know, the fluid is flowing between these two parallel plates is a viscous flow, and since the viscous flow is the laminar flow as well, and if we consider that flow is steady and uniform, then there will be no acceleration in the fluid flow, and hence the resultant force in the direction of flow must be zero. So considering this scenario, we'll get the equation equal to 0. So you can see here the P into delta y into 1 is the force acting on the face AB. Similarly, the another force acting opposite to that of flow direction, that is the second force. Because of it is acting in the minus opposite direction, here minus sign will come into picture. Similarly, another force, that is shear force, is acting on the face BC, and that too is the opposite direction, that's why this minus sign. And similarly, another force is acting in the direction along the flow, so this shear force will come as a positive. So upon solving these uh, equations, so we will get like as this one. So here I will explain one by one term. So these terms will come as it is here, and this whole area will multiply the whole bracket. So this P becomes P into delta y into 1, and this second terms become delta P by delta x into delta y into 1. Similarly, these terms will come as it is here, and the second terms will get multiplied by this area, and this area will multiply to this whole bracket, and the first term will become as tau into delta x into 1, plus the second terms will become delta tau by delta y into x into 1, and that will be equal to the 0. So if you see here, the terms which has got the opposite sign will get cancelled. So in this case, these first two terms will get cancelled, and second, these two terms will get cancelled. So this equation will become as a minus delta p by delta x into delta y plus delta tau into delta y into delta y into delta x is equal to 0. If we divide this equation by delta x into delta y, we are going to get is minus delta p by delta x plus delta tau by delta y is equal 0. This is simple mathematics, and finally you are going to get is the final equation, which is delta p by delta x is equal delta tau by delta y. And consider that this is equation number 1 here. Okay. Let us proceed with the first parameter, that is velocity distribution. As we know that from the Newton's law of viscosity, the shear stress tau is directly proportional to the velocity gradient, and it is represented by this equation, that is tau is equal mu into du by dy. Since this viscous flow is a laminar flow too, that this law will also applicable to this kind of flow. So therefore, if you take the previous equation what was given there, and we'll substitute this value of tau in the equation that is driven previously, so that equation will become delta p by delta x is equal delta by delta y. The tau value of tau will get substituted here, and it will become mu du by dy bracket closed, and upon solving that, these terms whole terms will become mu into delta square u by delta y square. Therefore, if you rearrange this equation, these terms will come to left side, and this mu will divide to left side of that equations. So it will become mu into delta square u by dy square is equal 1 by mu into delta p by delta y. So if we integrate this equation with respect to y, since this equation has square, to get the complete integration we need to integrate this equation two times. So first integration will come as delta u by delta y is equal integration of 1 by mu will be 1 by mu only, as it is constant term. Integration of dp by dy will be dp delta p into delta x, and y will come as a separate term, plus c1, that is c1 is nothing but a constant of integration. So this equation will again integrate with respect to the y only. So again integrate again integrating that equation, we are going to get the final equation is u is equal 1 by mu into delta p by delta x y square by 2 plus c1 into y plus c2. This is the equation what we are going to get after integrating that first integrated equation. So let us assume that this is equation number 2. So they here in this equation, the c1 and the c2 are the constant of integration, and their values we will obtain from the boundary condition. So in order to get the boundary condition, we need to assume this diagram. If this is a lower plate and this is upper plate, and distance between these two plates is the t. So if you see the boundary condition, first boundary condition will be at the lower plate, and second boundary condition will be at upper plate. So here if you assume the value of y, that is nothing but the value of t, and which is equal to 0 here. And as you know that along the boundary, while fluid is flowing from the any section as a pipe or a parallel plates, the flow along the boundary will be 0. The velocity of flow along the boundary will be 0. That's why u will be 0. So first boundary condition you can see here is y is equal 0, u is equal 0. So if you substitute this equation in the equation number 2 above, the it will become as 0 is equal 0 plus c1 into 0 plus c2. We will substitute this value in this equation. Upon solving this, we will get the c2 as a 0. c2 is equal 0. So again, if you substitute the value of upper boundary condition, where we are getting that y is equal to and u is equal 0 in the equation of this double integrated equation. So upon substitute, we will replace u by u0, 0, and mu will 1 by mu will come as it is. Similar dp by dx will come as it is, t square by 2 plus c1 into t plus c2. So upon solving this, we are going to get the value of c1 is equal 1 minus mu dp by dx into t square by 2 into t. So this t1 and this t will get cancelled, and the equation will become c1 is equal minus 1 by 2 mu into delta p by delta x into t, as this 2 will go here and it will become a 2 mu. You can see clearly here. So now we got the value of c1 and c2 from the boundary condition. This value of the c1 and c2 we are going to substitute in this equation. In this equation we are going to substitute it. So upon substituting this value in the equation number 2, as the c1 has c2 has the value of 0, so we are not going to do with that value of c2. So we'll substitute the value of c1 in the equation, and the equation will become u is equal 1 by mu into dp by dx into y square by 2 plus y into bracket minus 1 by 2 mu into dp by dx into t. So upon solving this, you can see here the 2 will multiply to this side, and equation will become u is equal 1 by 2 mu dp by dx will delta p by delta x will come as it is, and this y square will come as it is too. So y plus y into the bracket minus 1 by 2 mu delta p by delta x into t. We will take the common terms outside of this equation, outside of these two terms, and this equation will become u plus 1 minus 1 by 2 mu into delta p by delta x under bracket ty minus y square bracket closed, and we will give it as a equation number 3. This is nothing but the velocity distribution equation what we needed to study as a first parameter. So finally the velocity distribution we got this one, and so you can see in this equation the terms mu, the term dp by dx, and t are the constant. Since these are the constant, the velocity of the fluid flow will vary with the square of y. Square of y means it's nothing but the distance from the lower plate to upper plate in the y direction. So will vary with the square of y, and this equation is a equation of parabola. So the velocity distribution across the section of parallel plate is parabolic. So if you represent this velocity distribution equation in terms of diagram, it will become as this diagram. So here you can see the upper plate and lower plate. The fluid is flowing from left toward the right, and the velocity, that is u max, will be maximum at the center, and the velocity is going to decrease towards the lower and upper plate. Okay, so this is a velocity distribution. I hope you clearly understand it. Now we'll see the second parameters in this flow, that is the ratio of maximum to average velocity. So the velocity is maximum when the flow is at the center, that is nothing but y is equal to t. So you can see in this diagram, when the flow is at between the center, that is nothing but t by 2, the velocity is maximum. So u maximum will be there. So we'll substitute this value in the equation number 2, that is nothing but this equation, which is equation of velocity distribution. So here u max will be equal to 1 by 2 mu into dp delta p by delta x into t into y. Y will get replaced by this t by 2 here, and y square will be replaced by t by 2 square. So here this t by 2 has a whole square. So upon solving this, we'll get u max is equal to minus 1 by 2 mu into delta p by delta x under bracket. This t and this t will get multiplied, and it will become a t square by 2 minus t square by 4. So we'll take the common terms out of this bracket, and this equation will become the u max is equal 1 minus 1 by 8 mu into delta p by delta x t square. So we'll give the it as we'll give it as a number 3. So this equation is the equation of maximum velocity between two parallel plates. Then we need to calculate the average velocity. To calculate the average velocity, we need to divide the discharge across the section by the area of the section. The area of the section is nothing but T into 1. So consider that discharge Q will obtained by the rate of flow of fluid through a strip of thickness dy, and we will integrate it by the upper and lower limit. So upon doing that, we will get the rate of flow through the strip, that is nothing but dq into velocity at a distance y into the area of strip. So velocity at a distance y we will get by the equation of velocity distribution, that is nothing but this equation. So we will substitute this equation in this, and we will get it as dq is equal minus 1 by 2 mu into delta p by delta x in the bracket ty minus y square in bracket closed into delta y into 1. Delta y into 1 is nothing but the area of the strip. Upon solving this, we got this uh, velocity through the small strip. So in order to get the discharge through whole area, we need to integrate from between two limits, that is 0 to t. So upon integrating it, we will get it as q is equal minus 1 by 2 mu into delta p by delta x in the square bracket ty square by 2 minus y cube by 3 bracket closed between the limit 0 to t. So upon solving this t will get replaced in the place of y, and the equation will become q is equal minus 1 by 2 mu into delta p by delta x under the bracket t cube by 2 minus t cube by 3. So we will take the common terms out of this bracket, and this again it will become as a q is equal minus 1 by 2 mu into delta p by delta x into t cube by 6. So the final discharge through this two parallel plates for the viscous fluid will become as a Q is equal minus 1 by 12 mu. This 6 will multiply to this and it will become a 12, and 1 by 12 mu into delta P by delta X into T cube. This is a simple mathematics. Okay, so we'll see that we need to when we need to calculate the velocity from the discharge, we need to divide it by the area. This is from the continuity equation. So if we will divide this discharge what we have derived just now by area. So area is nothing but T into 1. So this T and this T will get cancelled, and the equation for the average velocity between two parallel plates will be equal to minus 1 by 12 mu into delta P by delta X into T square. So in order to get the ratio of maximum to average velocity, we need to divide the equation of maximum velocity to average velocity. That is nothing but we will divide the equation 3 by the equation number 4 what we have seen just now. So u max by u bar will be equal to minus 1 by 8 mu into delta p into delta x into t square divided by 1 by 12 mu into delta p by delta x. So this whole terms will get cancelled here. Similarly, this also 1 by mu will also get cancelled, and also this minus sign is going to cancel. So upon solving this, we will get ratio of maximum to average velocity is equal 12 by 8, and final we will divide it by the 4 and it will become a 2 and it will become a 12 become a 3. So we can say that the ratio of maximum to the average velocity when the viscous fluid is flowing between two parallel plates is 3 by 2. Understand? I hope it is clear for you. Drop of pressure head for a given length. If you consider the length L for the two parallel plates, so how much pressure is going to drop from section 1 to section 2 while fluid is moving from section 1 to 2. So in order to derive that, we need to have equation number 4, that is what we have already seen is u bar is equal minus 1 by 12 mu into delta p by delta x into t square. So this is equation of average velocity between two parallel plates. So we need to rearrange the terms in this equation. So that delta p will come to left side and it will be equal to 12 into mu into u bar divided by t square. So we need to integrate this equation with respect to x. Upon the integration will be in the limit 1 to 2. So upon integration we'll get, here you can see the integration equation, and we'll integrate this between the limits 1 to 2, and this equation will become as p1 minus p2 is equal minus 12 mu u bar into t square in the square bracket x1 minus x2. So p1 minus p2 is nothing but the pressure drop while fluid is moving from the section 1 to section 2. So in this term we can see that this sign is disappeared. So in order to do that, we need to exchange this x2 and x1. So this equation will become as p1 minus p2 is equal 12 mu into u bar divided by t square in the square bracket x2 minus x1. So this pressure drop, if we consider it in the terms of the pressure head, then this equation will become as hf is equal p1 minus p2 divided by rho g. So if we divide this pressure difference by rho g, this we will get the pressure head, the drop of pressure in terms of the pressure head. So it will be equal to 12 into mu into u bar by rho g t square into L. So if we ask how we how we came to know the L, about the L. So you can see here, this is a section 1 and this is a section 2, and the flow of fluid is from the left to right. If P1 is the pressure at the section 1 and P2 is the pressure at the section 2. So whatever the drop of pressure in between these two sections while fluid is moving from the section 1 to section 2. So this pressure difference we are going to get from this equation, and this L is nothing but the difference between these two sections, which is nothing but x1 minus x2 or x2 minus x1. So this is the final equation on pressure drop while viscous fluid is flowing between two parallel plates. So let us this equation assume as a number 5. Then the point number 4 about this analysis is the shear stress distribution. So it is the shear stress distribution is obtained by substituting the value of u from the equation number 2. So equation number 2 is about the velocity distribution that we already know, and it is equal to u is equal 1 minus 2 mu into delta p by delta x under bracket ty minus y square bracket closed. And from the Newton's law of viscosity for the viscous fluid is shear stress will be equal to the velocity gradient, and in this equation we are going to substitute the value of u. So upon substituting this value we will get tau is equal tau nothing but the shear stress is equal mu into delta by delta y under square bracket the value of u. The value of u is minus 1 by 2 mu into delta p by delta x in the bracket ty minus y square bracket closed. So we'll differentiate this equation with respect to y, and we will get that mu into the shear stress is equal mu into under bracket minus 1 by 2 mu into delta p by delta x under bracket t by 2y bracket closed. So the final equation about the shear stress distribution is nothing but tau is equal minus 1 by 2 delta p by delta x into t minus 2y. See, this mu and this mu will get cancelled. That's why this 1 by 2 comes directly into picture. Okay. So hope this equation is understood, and since this equation is the shear stress distribution equation and this is the final equation of this shear stress distribution, we'll name it as a equation number 6. So this equation of shear stress distribution, in this the terms dp by dx and t are the constant, and remaining is the tau. The tau will vary with linearly with this linearly with the y. Here you can see this tau is varying linearly with the y. Hence the shear stress distribution is shown in the figure, which is linear distribution. Here you can see that the shear stress will be maximum at the boundary layer, here at upper boundary layer and lower boundary layer. The shear stress is 0 at the center, since there is no viscous force available at the center. Here, hence the tau max at the boundary layer will be equal to minus 1 by 2 delta p by delta x into t. So this is the final equation about velocity shear stress distribution while viscous fluid flowing between the two parallel plates, and this equation we will name it as a equation number 6. So these are the 4 parameters to analyze the flow of viscous fluid between two parallel plates. Hope I understood it. Hope you understood it. And to summarize this whole video, we need to look at this slide. So first point we studied is the velocity distribution, that is u will be equal to 1 minus 1 by 2 mu into delta p by delta x into ty minus y square. Similarly, point number 2 what we have seen is the ratio of maximum to average velocity, and that is equal to 3 by 2. Then point number 3 is the drop of pressure head between two sections. It is nothing but P1 minus P2 by rho g, that is the pressure head, and it will be equal to 12 into mu into u bar by rho gt square into L. And fourth one is the shear stress distribution. Shear stress distribution will be given by this equation, and it is equal to shear stress tau is equal to 1 minus 1 by 2 delta p by delta x into t minus 2y. So these are the four important equations what we studied while analyzing the flow of viscous fluid between two parallel plates. I hope you enjoyed the video and learn about the scenario of viscous fluid flowing between two parallel plates. So if you like video, please share and subscribe, and thank you for watching the video.